Well, hello again. In this example, you will use the method of virtual work to calculate deflection quantities at select locations on a beam. Specifically, we are going to do virtual work using conventional integration, and we'll do so looking at this particular beam. A couple of things to notice right off the bat is I have already identified for us the coordinate systems that we're going to be using, and also the moment equations that are developed within this particular beam. What we want to do is we want to go ahead and use our basic statics to solve for the reactions. That's WL over 24, and the vertical reaction here, 7WL over 24. And we have this resultant here of WL over 4. And it probably shouldn't be a big stretch for you then to be able to see where these equations came from using these particular reactions and forces. I'm going to sketch what the deflected shape looks like for this. And then note that in this particular example we are being asked to find the vertical deflection at C and also the rotation at A. So we've got this vertical deflection at C, and we've got the rotation at A for which we are trying to compute things. The general virtual work equation that we will be evaluating is given as this. It is the integral of big M times little m over EI dx, where big M is the internal moment due to the real load, little m is the internal moment due to the virtual load. Since we already have the equations for the internal moment due to the real load, we are ready to move on to determining the equations due to the virtual load. So here's the virtual structure and the one that we would use to find for delta C. Notice what's happened. We have put a unit virtual load at the location and in the direction that we want to know the deflection. Using basic statics, we solve for the reactions here. And with a little bit of verification on your own, you can quickly find that these are the moment equations based upon these coordinate systems. Once you have that, you are prepared to write the virtual work equation. So 1 times delta C, so that's the external work, is equal to the internal work. So let's look at segment AB. That's going to be integrated from 0 to 3L over 4. We take the big M, multiply it by the little m, divide that quantity by EI, and integrate that with respect to x1. Plus, we get the other segment going on, so this is 0 to L over 4. Once again, big M times little m all over EI, integrated with respect to x2. One thing I'd like to make comment on are the coordinates that we are using here. So you may ask yourself, why did we use the coordinates like this? And with a little bit of experience, you'll find out different coordinates that you may be able to use to keep your moment equations simple. The only requirement that you are going to have is once you choose a coordinate system, say for the real structure like we have here, you have to use the same exact coordinate system for the virtual structure. So we now have these integrals, which can very easily be evaluated, as we've got here. We've got the two basic terms evaluated on their bounds, which comes up with what we show here, and that gives us a quantity of 5WL to the fourth over 2048 EI. The positive value says that we assumed the correct direction And how did we assume the direction? We assumed it with the direction of the arrow that we applied here. Okay, so that got me the deflection at point C, and now I'm prepared to get the rotation at A. And so once again, this is a virtual structure that will provide me little m. So I provide the rotation here at A. And before we do any other calculations, I do want you to notice something here. Look at the direction of the moment arrow that I provided. That actually is opposite the direction of rotation that we see on our deflected shape. And the reason I'm doing this is I just simply want to demonstrate how the signs of these things will indeed tell us the way things should be moving. Based on this applied moment, we can compute the reactions here, which would be 4 over 3L. And equilibrium then tells me that this has got to be 4 over 3L. And it is that which is used to develop the moment equations that we see right here. Please notice that for segment BC, the internal moment is 0. Thus, we can write our virtual work equations as follows. Integration from 0 to 3L over 4. We get the big M, negative WL x1 times the little m, which is 1 minus 4x1 over 3L. That's all divided by EI, integrated with respect to x1, plus 0 to L over 4. This is segment BC that we're looking at now. Big M times little m over EI integrated with respect to x2. Quick observation will tell us that this portion of the integral will head to 0. And so when I multiply out this numerator right here, I will get 2 terms up in that numerator, and that's what we're going to see here in this particular evaluation. Okay, so both of these are being evaluated from 0 to 3L over 4. You go ahead and evaluate that, and it computes out to be negative WL cubed over 256 EI. The negative means that I did indeed assume the wrong direction. Notice I assumed clockwise here, so that means that really it's rotating counterclockwise. That concludes this example. As always, it's a beautiful day to study structures.